Hi everyone. In this video we are going to be going over section 4.2 in your textbook, which is going to be about actually building a linear regression model based on your data so that we can make predictions. Okay. So as a little bit of background before we get started, what you're looking at on this slide is called the slope-intercept form of a line. So for any given line that you have on the xy plane, this formula can be used to describe that line, where m is what we call the slope, and b is what we call the y-intercept. And so the y-intercept is where your line passes through the y-axis. And if you know those two things about your line, then you can always use this formula to plot your line on your xy plane. And the only line that you can't really get is vertical. And so hopefully this is just a review of what you already know from algebra. Now suppose that you do work for Texas Tech University. Suppose that maybe you're like the dean of the College of Engineering or something like this. And basically, you don't want to admit any student into the chemical engineering program unless you predict that he or she is going to succeed in the chemical engineering program. So basically, you don't want to be allowing a lot of students to join the program if in the end you think that they're going to be unsuccessful, right? Because that would be a waste of the student's time, it would be a waste of the professor's time. And in general, what you want for the chemical engineering program is you want the success ratio to be very good. So the ratio of students who actually succeed with the program to the number of students that join the program, you want that to be higher so that prospective students would be like, yeah, this is a program that, if I'm accepted, I can actually be successful here. You want the potential students to have that confidence. So what you decide to do is you create what is called a pre-engineering course. And this is going to be a course for freshmen that they take their first semester. And they're not actually going to be admitted into the chemical engineering program yet, technically, until after this pre-engineering course. And what we're going to do is we're going to sort of set up an experiment. And in this experiment, well, it's not, maybe I misspoke. It's not quite so much an experiment as just a study, because we're not actually going to give different groups of students different treatments, but all we're going to do is set up a study where I measure every student's term grade just from the pre-engineering course. And I measure the student's overall chemical engineering GPA after their graduation. So after 4 years, when they're finally graduating with their chemical engineering degree, I look at their entire program GPA. We're asking which is the response variable and which is the predictor. Actually, we say that the student's term grade in the pre-engineering course is the predictor variable because we want to be able to use that variable to predict the overall program GPA of a student. And you'd probably, also include students who didn't make it to graduation, right? So that you are including the students who are not successful in your study results. So here we go. Let's say my n, my sample size, lowercase n is always sample size, is 100. So I have 100 students that I tracked through their 4 years. And here I've plotted their pre-engineering term grade on the horizontal axis, and the vertical axis represents their program GPA after they are done with the chemical engineering program, right? So anyways, you can see each dot is going to represent a student, and so every student has both a term grade from pre-engineering and a program GPA. And it turns out, if you go through calculating what this is, this lowercase r, which is the linear correlation coefficient, then we find that R is 0.894, which means that there's actually a very strong correlation, a strong linear positive correlation between these two variables, like we might expect. And not only do we want to see that there's a correlation, but we also want to build a model. Now, a model is just a mathematical function that is created from data. We're basing our model in the data we collected. The simplest possible model that you could hope to make is this right here, where I say y hat equals y bar. So y hat, that is a prediction that you're making for the value of your y variable. And y bar, remember, is referring to the sample mean of the y variable from your data. So the simplest possible model, you could say, is that, your response variable, our prediction for your response variable for some new experimental unit, is just going to be equal to the sample mean of the y variables that we measured for all of the experimental units we've already measured. That would be the simplest possible model, is just to assume everything, our prediction for everything is just going to be the mean. And so in our case, that would be to assume that any new student's GPA is going to be the mean program GPA, which is 45.7, right? Just assume that if any student walks into your office and says, hey, I'm thinking about joining the chemical engineering program, your prediction is immediately that student's program GPA will be 45.7. To just kind of give you another example, this simplest possible model, this would be the equivalent of being like a weathercaster or like a meteorologist on the TV who every single day predicts that the high for the day, the high temperature for the day, is going to be 70 degrees Fahrenheit. And never, ever, ever changes the prediction. Every single day, the high for the day is predicted to be 70 degrees Fahrenheit. And the reason being because, well, if I take the average of all of the, highs for the days since we've started measuring, maybe in this one city, the sample mean was 70 degrees Fahrenheit. So we'll just assume that every day going forward is 70 degrees Fahrenheit. So it's a simple model, but it's also not a very good model, because what we want is a model that actually produces better predictions by actually making use of the predictor variables. So in the case of weather, a predictor variable might be, do we have a cold front blowing in? Do we expect, clouds to be in the area? What's the humidity like? What are wind speeds in the region like? What are the wind directions in the region like? This sort of thing. And so in weather, you can actually use different predictor variables to have a better prediction of your response variable. And likewise, we are not going to settle for this simplest possible model, and instead we're going to improve on it. Because applying the simplest possible model would look like this. So in orange, we have a visual depiction of the simplest possible model. So if I just assume that regardless of any student's pre-engineering term grade, I always assume that any student is going to have a program GPA of 47, it would look like this horizontal orange line, right? So it doesn't matter to me whether you got a 90 in pre-engineering. I'm going to predict that you will get a 47 program GPA. It doesn't matter to me if you got a 10 as your pre-engineering term grade. I'm going to predict that you will end up with a 47, program GPA. And that just doesn't seem to make a lot of sense, right? If we have the data available to us and we know what the student's pre-engineering term grade is, that should give us a better feel for what their program GPA should be. So we should be able to make a better prediction. Before we move on, I want to point out a vocabulary word. This difference right here between a measurement of the response variable and the mean, well, let me take that back, not the mean, but the prediction of the response variable. So I might call this y subscript I, so that's one of my measurements for the response variable. And my prediction would be y hat I. This is what we call a residual. And we use E with a hat on it to represent the residual, because what this is saying is this is the, excuse me, I can't write and think at the same time. This is going to be a prediction of the error. Or maybe I should say, this is going to be the error of the prediction, right? Because if y hat is my prediction and y is an actual measurement taken, well, then E hat is going to be the error of the prediction. And so remember, hat means prediction, and in this case, lowercase e means error. And so the residual is the error of a particular prediction. Okay. And so again, this E hat down here, this is just a different measurement yi, and then still, with our simplest possible model, this is the prediction here. And so the difference between the measurement and the prediction, this is what we call the residual. Okay. Now the next simplest model, so still trying to remain as simple as possible, but also we do want to be more sophisticated than that constant function, because we talked about how that was sort of not very helpful, is what we call the linear model. So in the linear model, remembering that a line on the xy plane we can represent as y equals mx plus b, that should look kind of similar to where b1 is going to be the slope now, of this linear model. We're going to use b with subscript 1 to be the slope of the line, and then b with subscript 0, that's going to be our new y-intercept of this line. But what I'm saying is this y hat, which is a prediction of our response variable, a predicted value for that y variable, depends now on x, which is our predictor variable, or our explanatory variable. Remember, predictor and explanatory are synonymous in this case. So the prediction is going to be actually a function of our predictor. That shouldn't be surprising. So in our case, if we want to build this type of linear model, what we will get is that the program GPA is going to be 1.12 times the pre-engineering term grade minus 19.3. And so here, this 1.12 is going to be my b subscript 1 coefficient, and negative 19.3 is going to be my b subscript 0 coefficient. And you can see that the x value, my predictor value, is the pre-engineering term grade, and the program GPA is what we want to make a prediction for. Okay, so now here in green, this green line represents our linear model given by this formula here. And so now if you tell me a student's pre-engineering grade, that actually affects what I predict for their program GPA. So if you tell me they made a 30 in pre-engineering, then I can predict that they're going to make something around like a 15 for their program GPA. And if they make an 80 in pre-engineering, I can predict that they're going to make something like a 70 in their program GPA, right? And so this green line actually allows me to make a more accurate prediction because I'm actually taking into account the fact that students have a different pre-engineering term grade. And that may, again, that may be the whole purpose of the pre-engineering course, is to get a feel for how well the students are going to perform. Now again, the residuals are going to be the difference between one particular measurement and the prediction that you would have made for that measurement. And so we actually do still have some students that might make like a 55 in pre-engineering, and for that we predict that they're going to make like a 42 as their program GPA. And yet there's a difference here, right? So we actually have this student who did relatively poorly in pre-engineering, but then got a really excellent program GPA. And so the difference between actually the measurement and the prediction that we had for that student, that difference is going to be what we call the residual. We use E hat to mean the residual. So each one of my measurements has a residual. I have 100 residuals I can calculate. Just be aware of that. There's a different residual, but this one's smaller for that measurement and that prediction. The difference is still the residual. And you might be wondering at this point, that green line really does look like a good linear model given the blue measurements. But how did we calculate this line? And also, in a similar vein, you might ask, why is that particular line the best choice? Because whenever you're drawing a line, there's a bunch of different lines you could draw here. You could draw that line instead. And what makes this light green line better than the dark green line I just drew? Or maybe you might think that, hey, this purple line that I'm about to draw, that line is a better linear model than the green line we already have on here. In other words, what makes that green line the best choice, right? We always want to make the best model as long as we're going about making a predictive model. And so how do we know that's really the best choice? There's not some other model that would be doing a better job. And so I'll try to answer these questions as best I can. Since we want the best model, notice that anytime you hear the word best, we're talking about an optimization problem. So this is a specific kind of math problem that you can study if you want to, but we're trying to optimize our model. We're trying to choose the best model. And in mathematics, we're going to describe any optimization problem just as a matter of either maximizing or minimizing some criterion. So we have to decide, what am I going to maximize or what am I going to minimize? And once I've decided that, we actually can use mathematics to figure out what the optimum solution is. And I want to remind you of a few things. So as a reminder, a deviation is the difference between a particular measured value and the mean. So remember the hat, or sorry, not the hat, I misspoke. The overbar here is referring to the sample mean of all of the response variables. And the SST stands for sum of squares total, is actually the sum if you take all of those deviations for every measurement and then you square it. Right, so this is SST. The residual now, so moving past reminders and now teaching more stuff. Well, actually, this is kind of a reminder from 5 minutes ago. The residual is the difference between a measured value and the predicted value. So y hat is telling us that this is a predicted value. And then SSR is now the sum of squared residuals. And you might sometimes see this as RSS. So I apologize if I use both of these acronyms interchangeably. Really, it depends on which textbook you're reading from, if you see SSR as the sum of squared residuals or RSS. But they mean the same thing, just so you know. But the sum of squared residuals is just taking the residual and then squaring it and then adding all of them up. So kind of analogous to SST, but again, now we're taking the difference between a measured value and the predicted value, not just the measured value and the mean. I also want you to remember that the sample mean, which was the expected value for some random process of one variable, that sample mean solved the particular optimization problem. The sample mean minimized SST. And I showed you this on, I think, the video about section 3.1, how the sample mean is actually the point that minimizes this SST function, which I've shown in blue here. Well, now what we want to do is not minimize SST, but we want to minimize that sum of squared residuals. Basically, we want to find these coefficients, B1 and B0, such that this model is going to minimize the sum of squared residuals. Because remember, I can define any line by just choosing different coefficients b1 and b0, and so I can sort of summarize this task that we have ahead of us as being like, we want to choose a particular b1 and b0 that minimizes the sum of squared residuals. So we've now really defined really well what our optimization problem is. And I'll show you that Excel has a nice solver tool, and it can solve a lot of simple optimization problems, like our optimization problem of choosing b1 and b0. And so let's do that first. This is an Excel workbook, and what I'm going to do is I'm going to come up with some x variable values, and remember x is representing our predictor variable, which is the same thing as an explanatory variable, all equivalent. And just because we're trying to keep this simple, my x values are going to be 2, 4, 6, and 8. I'm also going to come up with a y variable. So we're talking about two variable statistics here in chapter 4. So I have a predictor variable and a response variable. And then this response variable, remember, this is basically saying what I am trying to predict. And let's say that for each of these, I have a y measurement of then like 1, 3, 5, and 6. So this would be two aspects of the same experimental unit, by the way, right? And so to make use of a previous example I gave, the predictor variable might be something like the number of days of class a student attended. And the y response variable, that might be something like the number of questions the student, got correct on an exam. And so I want to be able to use my predictor variable to predict my response variable. And what I want to do here then is I want to make a linear model that will tell me my predictions given a response variable. And my linear model here is that y hat is equal to b subscript 1 times x plus b subscript 0. That's my linear model that we've been talking about. And I'm also going to have to make a space, I guess, to really define what is b1 and what is b0. And I'll let them both be 5 just for right now. So to calculate my y hat, I'm going to take b1 times my x value plus b0. And I don't want those references to move around very much. So where it says D9 here, I'm going to use dollar signs to make sure that cell reference doesn't move. And where it says D10, I'll use the same thing. I'll use dollar signs. And now what I have is I have my linear model producing estimates of what my response variable should be, only based on looking at the predictor variable. But these aren't very good predictions yet, and they're not very good predictions because I haven't tuned, or I haven't actually found the right optimum values of b1 and b0, right? So I still have a task ahead of me, and that task is finding these optimum values to tune my model. So I'm going to make another column, and this is going to be the residuals. And remember, the residuals are just going to be y hat minus what I actually measured, or I think earlier I put it the measurement minus y hat, the measurement minus the prediction. So I'll take my measurement minus my prediction for each of these 4 measurements. And so I have the residuals then calculated. And then I'm also going to calculate squared residuals just by taking the residual next to it and squaring it like this. And the last thing I'm going to do is I'm going to take the sum of those squared residuals, which we call SSR. And that sum then is just going to be equals sum, open parentheses, and then select that region with all of the squared residuals. So here is the sum of squared residuals, 3,101. Now, like I said, what we're trying to do is find values for these coefficients, b1 and b0, that lead to the minimum value of SSR. And so the way I can do this, I'm actually going to go up to Data on the ribbon, and then over to Solver, and this is the Excel Solver tool I've been talking about. Clicking Solver, it says it wants me to set an objective, so I'm going to set objective to the F3 cell, which is where I have calculated my sum of squared residuals. I want to set that to a minimum value, and I'm going to do this by changing these cells right here. So I select where my B1 and B0 values are. And this is pretty much all I have to do. I'm going to make sure that I uncheck this box that says make unconstrained variables non-negative. I'm okay with having negative coefficients, and so I'm going to uncheck that box. I'm going to click Solve. And then I'll keep Solver Solution, and you can see that now my sum of squared residuals is actually quite small. And my predictions are relatively close to what I had measured for my response variable. So where I had a response variable measurement 1, my prediction was 1.2. Where I had 3, the prediction is 2.9. And where I had 5 is now 4.6, and 6 is now 6.3. So not too bad for predictions. And again, we're trying to get predictions that are as close as possible to what we get when we measure the response variable. In a real-world situation, this is never going to be perfect because our measurements introduce some kind of noise. They're never going to be a perfect linear process that we're measuring, but this is the idea. So now we know B1 and B0. Now we've created a linear model, because just knowing these coefficients and knowing the formula here for a line, that allows us to have a mathematical function that will produce predictions when we know the predictor variable. Okay, so that's one way to do that. This is what I just demonstrated, the solver tool. This is what we just did together. And the next thing we're going to do is in Excel, we're going to create a scatter plot and see if we can find those coefficients by an even easier method using Excel. So now that we know what's going on, let me just show you that if I grab these range of values here, and I go up to the ribbon and click Insert, and then Scatter Plot, get rid of the chart title, and there's some other, by this point you know there's some other cosmetic things I don't like about the default Excel scatter plot, but I'm ignoring those for now because I just want to click on one of the measurements, one of the data points here, and I'll click this plus button and then add a trend line like we've done before in the previous video. And then I'm going to use this little arrow to the right, and where it says more options, I'm going to click this. And then going down to the bottom where it says display equation and display R squared value on chart, that's what I'm going to click. And now check out this right here. This is telling me that my formula for my linear model should be this. It should be y equals 0.85 x minus 0.5. That's what it's telling me that the best linear model is. That linear model given by this line that sort of passes through the midst of these 4 data points. And let's compare it to what we found earlier using the solver tool. Well, yeah, it actually works really well because my B1 coefficient is basically 0.85 and my B0 coefficient is again basically negative 0.5. So it looks like we found the same answer whether you do it with the scatterplot tool in Excel or whether you do it with the solver tool. Okay, having done that, I'll point out that your TI-84 calculator can also calculate these optimal coefficients. And so let me pull up your calculator and demonstrate this. So I'm going to go to Stat button and Edit to get back to my lists. And my list of data that I have been using, in list 1, I'll put the predictor variable values. So I'll put 2, 4, 6, 8. And then for list 2, I'm going to put the values of my response variable. So I'll put 1, 3, 5, 6 like this. Hopefully you can see what's going on in the calculator. Hopefully you're following along so you know how to do this on an exam. I'm going to go back to stat. One arrow over to calc, and then I'm going to go down to number 4 where it says linreg, saying linear regression. So I click enter here. It's going to ask me what lists I want to use, but right now it's set up correctly, so I'm going to go down to calculate and click enter. And here we go. Again, what your calculator has found is that the slope of your line of linear regression should be 0.85, which is exactly what Excel told us. And the constant at the end, the y-intercept of our linear regression model, should be negative 0.5, which is, again, exactly what Excel found. So that's just how you do it on your TI-84 calculator. And you're going to be able to use this calculator on an exam. And so I want to make sure you know how to do it using your calculator. By the way, it wasn't a waste of time to show you on Excel because I do expect you to use Excel for your project that I'll be introducing next week. And so be aware that you have this project this semester about linear regression. And whenever you're making visuals for your paper, you're going to want to use Microsoft Excel. So my last bullet point here, now that we've shown how to do this on your TI-84, I want to show you how would you do this if you were stranded on a desert island, meaning you don't have a TI-84 with you, or if you do have a TI-84, maybe it's out of batteries, right? So if you were by yourself, how would you calculate the optimal coefficients? And the answer is going to be these formula right here. So this first line is just reminding you what does it look like when you have a linear model. That is, your prediction for your response variable is equal to B1 times your measured predictor variable plus B0. And then these formulas are actually going to give you the value of B1 and B0, right? So that's telling us what we need to find in order to use our linear model. And some familiar characters pop up here. So remember, R is the linear correlation coefficient, which we learned how to do in section 4.1. You learned how to calculate this. And that wasn't easy. That took quite a bit of time because we had to calculate z-scores and whatnot. This S with subscript y, this is going to be the standard deviation, by the way, the sample standard deviation of your response variable measurements from your data set. And then this S with subscript X, again, sample standard deviation, but this is going to be the sample standard deviation of your predictor variable measurements from your data set. And then down here, y bar, that's the sample mean of what? Of your response variable. And the x bar is going to be the sample mean then of your predictor variable. So let me use Excel really quick, I suppose, just to demonstrate that these formulas work and that you can actually use these to get exactly the same coefficients as before. So in Excel, I'm going to take a quick shortcut because you've seen last video how to do this. For my linear correlation coefficient, I use lowercase r to denote that. This is going to be equals CORREL, and then I select my predictor variable and my response variable data. Close parentheses, enter. So that's a lowercase r. Now, what am I trying to do? Oh yeah, calculate B1 and B0, but now I'm calculating it by hand. Oops. Calculating this by hand. B1, the formula. Oh, I need some other things too. Hold on. Because I'm going to need the x mean and the x sample standard deviation. And also the y sample mean and the y sample standard deviation. So for the x sample mean, I'm going to type in equals average A4 through A7, and it also gets me the y sample mean if I copy and paste it there. And for the x sample standard deviation, equals stdev.s. Make sure you're getting the sample standard deviation, and there we go. Oops, I did this again. So I have the means and standard deviations, and that should be all I need now to calculate B1 and B0 by hand. Just remember before when we found these, it was using the solver tool. Okay, so back to our formulas. B1 is going to be R times Sy over Sx. R times Sy over Sx. So this is equal to R times Sy divided by Sx. And then B0, that is y bar minus B1 x bar. So this is going to be equals y bar minus B1 times x bar. Boom. You can see we got the same values now that we've found before already 4 different ways. But it's nice to see the different ways to do it, because I'm sure that I will ask you to do it, you know, different ways on your exam. Like on your exam, I'll probably ask you to find it on a TI-84 calculator and ask you to find it by hand. And also on an exam, or not on an exam rather, but during your project, you'll probably want to use these 2 methods for your project. Okay. Now, things to notice about linear regression is that B1, the slope of the line, B0, the y-intercept. The slope is going to be positive whenever my linear correlation coefficient is positive, because your standard deviations are always positive. I promise. Because what do you do when you find the sample standard deviation? I invite you to look at your formula chart. But you actually take all of the deviations and then you square them, and that makes them all positive. You add them up, you still have a positive number. You divide by the sample size, still a positive number, and you take a square root, which is still a positive number. So this fraction, a positive number divided by a positive number, is always going to be positive. And so the slope can be either positive or negative, but the slope, the sign on the slope, only depends on the sign of your linear correlation coefficient. So that means if you have a positive association or a positive linear correlation coefficient, that means you will have a positive slope of your linear regression line. And then, of course, if your association between your variables is negative, then that means the slope of your linear model will also be negative. Okay, that's important. And then notice the point, x bar, y bar is always on the line. So remember, the bars mean the sample means. But this is important. I guarantee you I'm going to include a question about this on your exam. So make sure you know this. That point should always be on your linear regression line. And you might ask, why do you say that? Well, just take this right quick. And for both sides of my equation, I'm going to add B1 x bar. Ooh, so when I add B1 x bar to both sides of the equation, what I find is that y bar is equal to B1 x bar plus B0. So in other words, when I take my linear model up here and I let this point happen, so I let x be x bar and I let y hat be y bar, well, what I get, that's actually guaranteed by the way that I'm calculating my B naught coefficient. And so, that's how I know. That's how I know that this particular point has to always be on the line. So, some interpretations that you might be asked about on homework. Y hat is an estimate of the expected value of your response variable given a specific value of x, where x is your predictor variable. And remember that predictor and explanatory are synonymous. B1 is the ratio of change in y to change in x. So the ratio of the change in your response variable to the change in your predictor variable, that's what B1 means. And B0 is going to be the value of your prediction whenever your predictor value is 0. So let's talk about this. How to use this model. We know we've talked about building this model, but we also need to know how to use it. If a freshman student gets a term grade of 72 in the pre-engineering course, what GPA would you expect him to finish with at the end of the chemical engineering program? Well, my GPA, remember this is a prediction, my predicted GPA for this particular student is going to be 1.12 times 72 minus 19.3. So, putting this in my calculator, this is the easiest part of, learning about linear models, is just using them. 1.12 times 72 minus 19.3. That tells me my prediction for this student's overall program GPA would be 61.34. Okay. For any 10-point difference in term grade for pre-engineering, what does that translate to in terms of a program GPA? So I'm talking about a difference, not a specific term grade, but I'm talking about a 10-point difference in term grade. So let's think about this for a moment. We're going to have one student who has a particular term grade in pre-engineering and another student that has a 10-point difference. And we're going to see, what does that do to their program GPAs? Right? So just for kicks, my first student that I'm thinking about, let's say they have a term grade for pre-engineering X. I'm not very creative, I'm just calling it X. My second student, they have this same term grade plus 10 points. So their term grade for pre-engineering is going to be X plus 10. Okay? And what I'm concerned with is what is going to be the difference in their overall program GPAs. They had a 10-point difference in term grade. What's their difference in program GPA? And so what we're going to do is we're going to plug in their term grades into my model here and see what happens. So for the first student, I'm going to use a subscript 1. And so I'm going to let y hat 1 equal 1.12 times x minus 19.3. And for my second student, I'm going to let y hat 2 be their prediction. So it'll be 1.12 times x plus 10 minus 19.3. And again, what I'm interested in is since the second student's term grade was 10 points higher, how much higher is that second student's program GPA going to be? And so I'll take the difference of their predicted program GPAs. And for y2 hat, I have 1.12 times x plus 10 minus 19.3. And for student number 1, I have minus 1.12x. And then I'm going to keep parentheses around this for now because, oops, that should be 19.3, not 1.93. Because what's inside the parentheses, that is going to be y1 hat. I'm subtracting the two. Now notice I I can distribute this 1.12 and get 1.12x plus 11.2. And then I will be subtracting 19.3 here. And also later, I'm going to be adding 19.3. And again, I'm sorry about this, but there's a typo here. Not a typo, but I miswrote something. y1 hat is 1.13x minus 19.3. So this in parentheses, this is y1 hat. And so when I distribute this minus sign, it'll be minus a negative 19.3. And so those are actually going to cancel out. So I've written down in red, that's going to cancel out. And then I'm also going to have minus 1.12x. Now you'll probably see that this 1.12x minus 1.12x is going to cancel out. And it turns out this difference of y2 hat minus y1 hat is going to be 11.2. So whenever I had two students that started off with a 10-point difference in the pre-engineering term grade, they ended up with an 11.2 difference in their program GPA. So this is the answer to our question. Okay, now for a student with a 0 term grade for pre-engineering, what does that translate in terms of predicted program GPA? Well, let's just use my model here. Their pre-engineering term grade was 0. So that means their predicted program GPA is negative 19.3. And you'll notice that you can't really have a negative GPA, right? Like the lowest you're going to get is a 0. So this doesn't have an application in this particular setting. So sometimes this y-intercept, this b0 coefficient, sometimes that has a meaning that you can really interpret. And in this case, it does not have a meaning. So it only sometimes has a real interpretation. But a lot of times it doesn't. Now, you have to be careful, like I said, when we're talking about that y-intercept. You have to ask, is 0 a reasonable value for the predictor variable? And do enough observations near 0 exist in the data set? And those are both maybe important questions. Like, if I go back to our data set, we didn't actually have many measurements near 0 in our data set, right? Like the student with the lowest pre-engineering term grade had like a 25 or something like this, right? So I'm looking at here. And so, we don't have enough measurements close enough to 0 in our predictor variable. And so that's going to immediately invalidate any interpretation of the B0 y-intercept. But the other question they ask on this slide, I say the question they ask, I actually wrote these slides. The other question I asked here is 0 a reasonable value for the predictor variable? And 0 would mean getting a term grade in pre-engineering of 0. And getting a term grade in pre-engineering of 0 is probably not a reasonable value, because in order to earn a 0 in a course, you just have to be completely not participating in the course. And so if you're asking what would be the program GPA of a student who did not participate at all in the pre-engineering course, well, without having them participate in the course, you don't really know what they're capable of doing or what their performance might have been. And so you can't really use our model if you don't have that information. And so I would say no to both of these questions. And so if you say no to either one of these questions, basically your interpretation of the y-intercept is not going to be valid anyways. So let's talk about interpolation versus extrapolation. And so this is a completely new example. Forget the previous one. Here, these blue dots again represent some measurement of a predictor variable and a response variable. And what we've done with this line is we've said, well, this line is our model. It's our linear model that we've built. And the linear model looks like an excellent linear model as far as matching up with the measurements we've already taken in our data set. But I show you this for a reason, and that reason is, when should you use your linear model and when should you not use it? And here's the point, is that interpolation is good. Interpolation means that you have a predictor within the given measurements within the data set. And like, an example of this might be like, if your x value here was going to be 775. If I use this model to create a prediction of my response variable, it would tell me the prediction would be something around like 390, I don't know. And we would actually be able to trust this interpolation. So an interpolation is when you use the model and you make a prediction, but you're using the model with a predictor within the given range. And what I mean by the range is like, here's the top end of my data set and here's the low end of my data set in terms of my predictor variable. Extrapolation is doing not that. So extrapolation is generally bad, and it's bad because it's unreliable. So what I mean by extrapolation is like, suppose I want to use this linear model that I've made, but I have a predictor value of 1025. And so I'll use my linear model, and so I'm making a prediction using my linear model. So I trace it up here, and I go out across. And I get a result of like 510 for my prediction, and it's okay. My linear model made a prediction given a predictor value. But this is going to be really unreliable. And why? Well, when we built our model, when we trained that model, we didn't actually give it any data in this range. And so while we really know with a high degree of confidence that the behavior is linear down here for lower values of our predictor, whenever we get into these high values of our predictor, we actually have no guarantee that our data remains linear. Something that might happen is this. And this would be very, bad for your predictions up high. But what might happen is that maybe the data is increasing for certain values of your predictor, and then maybe it turns around, and then maybe your values start to actually get lower for an increasing predictor value. And in that case, your prediction that we made when we extrapolated is going to be way far off of what it should have been. We have this huge discrepancy between reality and our model. And this comes about because we can't trust extrapolated predictions. We can really have a lot of confidence in interpolated predictions, but extrapolated predictions not so great. You may, if you're an engineer or working in some other kind of field, you may run across situations where you want to make a prediction that it's just barely outside of your data set. Like if your predictor is like 915 or something like this. You can make a prediction that's just like, okay, it's kind of in this zone that's like technically extrapolation, but also mostly trustworthy. You can't trust it quite as much as a true interpolation, but for the most part, you'd be able to trust something that's extrapolated just outside of your data set. I'm going to give you an example to, again, illustrate with something actually quite realistic for why you should not trust extrapolated predictions. And so here's the example. At a ranch in England, there are 10,000 total cows. On week number 0, so I'm numbering the weeks, and I'm numbering this particular week, week 0, 1 cow is diagnosed with mad cow disease. 1 cow out of the 10,000 cows. Now, the outbreak isn't controlled, so they're not going to do anything immediately to make sure that this disease doesn't spread among the cows on the ranch. And so epidemiologists are going to show up around week number 30, basically to study the spread of the disease and see what they can do to help or to stop it. So they show up on week 30. On week 0, that's when the first cow gets the disease. On week 30, that's when they actually start, studying the spread of the disease. So after the epidemiologists show up, we have this table of data. On week 31, the number of sick cows is going to be 1,885, and on week 32, it's going to be 2,297, and so on. And so they make this table, and they use that table here. So this is going to be on the x-axis number of weeks since the first diagnosis, and on the y-axis the cumulative number of cows diagnosed. And so each blue dot here corresponds to one row from the table. Like this row from the table represents that dot, for example. And what I would say, looking at these dots, these 10 measurements, I would say, hey, this is an almost perfect linear association, right? I mean, you could draw a line straight through those dots and they would all pretty much fall directly on the line. So this is almost perfect fodder for building a linear model, you might think. And so you do. We build a linear model and we say that, well, my B1 coefficient is going to be 569, my B0 coefficient is going to be negative 16,000 or something like this. And again, looking at that line that passes through those points, you're like, man, that's a good model. Let's answer these questions using our model. How many cows will be diagnosed after week 44? And so we're extrapolating a little bit, right? When we ask about week 44, and we've only witnessed week 40 as the maximum, or the top of the range of my predictor variable, asking about week 44, that's an extrapolation. And so let's do that though. Might as well. Gotta try it. So we're going to have 569 times 44 minus 15933. So the predicted number is 9,103. And for week 50, we do the same thing. So 569 times 50 minus 15933. And I get 12,517. And next question, how many cows were diagnosed after week 29? So looking retrospectively, we didn't actually have a measurement for week 29 out here, but supposing we did measure, what would we have found for week 29? It will be 569 times 29 minus 15933. Well, we could say we probably would have found, according to our model generated the prediction that we would have found 568 cows diagnosed with the disease at week 29. And let's ask about week 27 now. So about week 27 times, 569 times 27 minus 15933, negative 570. So when I used my linear model to make a prediction about how many cows were sick on week 27, it was negative 570. But wait, maybe it occurs to you that you can't have a negative number of cows diagnosed with a disease. And moreover, we know that in week 0, we had one cow diagnosed, and the way that diseases spread, you would expect that each week after week 0, that you would have a number of cows that's actually growing in number that's diagnosed. The one cow spreads the disease to maybe 2 other cows, and then you have 3 sick, and so on. So you expect the number of cows sick to be increasing week after week. And so really, it should make you upset to see negative 570 cows as a prediction for week 27. So that's clearly bad, and clearly because we extrapolated and we didn't interpolate. Again, let's talk about week number 50. I tried to sneak this past you, but maybe if you are really astute, you notice that there's 12,517 cows sick for week number 50. Part of our problem statement was that there was only 10,000 total cows, and so we could not have 12,517 cows sick. But again, that's what our model predicted, again, because of a bad extrapolation. So this is also clearly bad. Meanwhile, just to point out that if you were to interpolate, this would be a great model, right? With interpolation, models work really, really well. So like if you wanted to interpolate for like 35.5, like halfway through week 35, how many cows would be sick? Like that would be a really great prediction. That would be something that you could rely on, and it wouldn't be unreasonable at all, because it would lie somewhere between the week 35 and week 36 predictions, which were measurements, so they had to be reasonable, right? So interpolation, good. Extrapolation, bad. That's the point I'm trying to make here. And I want to point out that this really is a realistic data set. So what we have here is weeks 31 through 40, 10 measurements, 31 through 40, and those measurements came directly out of this right here. So here is week 31, and this is week 40. And my point is that if with this wide picture view of things, when you actually see this, you say, well, this curve is clearly non-linear. So in reality, the number of cows diagnosed never exceeded 10,000, and it never went negative. At week 0, you only had 1 cow diagnosed, so that's pretty small, but it never goes negative. And at some point in the future, you would expect all of the cows, all 10,000, to be diagnosed. But in between, this curve is actually not a perfect line, right? So we don't make a straight line from 1 to 10,000, but it actually takes on a sort of curve. But even nonlinear curves can appear linear whenever you zoom in. So over small ranges in your predictor variable, this can look linear. So we actually did just draw a line between 31 and 40, and you can draw a relatively straight line through those points and actually capture all of them. But clearly, you can't expand that linear regression and expect it to extrapolate well. This is the point. Okay, sorry for such a long video, but there's, like I said, in chapter 4, there's just so much good stuff, and it's so directly applicable to, things that we see in life. And if you've ever wondered about machine learning, how does a lot of machine learning work? How do we make predictions? A lot of predictions are made based on regression, and regression is really a staple or a cornerstone of machine learning. So if you want to go into like data science, data analytics, regression is something that you definitely study, and it's definitely used very frequently in engineering and in the tech industry and all over. So I'll see you in the next video.